So chapter 7 on functions, limits and continuity. What we start with, and in this chapter there's quite a lot of this, a bit of revision of stuff that you will have already seen in first year, though perhaps not done rigorously, but still with some elements of rigour, and the notions of functions of several variables and what it means to have function limits or continuity in that setting. So first of all, what is a function? Actually, there's a rigorous pure mathematical definition of function that I won't trouble you with, but if you were worried about the sort of mathematical foundations of the subject, you might want to go away and find out what a pure mathematician really says a function is. But for the moment, we'll just say that we know what it means. It means that you've got a couple of sets, a domain A and a codomain B, and a function from A to B where it assigns to each element of A exactly one element of B. So you know what this rule is, and you take a point in A, it'll pick out a point of B for you, and that's what your function does. So A gets mapped to f of A. We're not allowing things that take more than one value, so we won't allow plus or minus square root. In this module, when we use the square root function, we mean the non-negative square root function, otherwise it wouldn't be a function. If you've got a subset of your domain, you can restrict your function to it, and you get the restriction denoted by f restricted to s with this line here, and that's the same rule, but you just apply it to fewer sets, fewer elements. And then sometimes you want to know which points can you get to using your function, and you get the notion of the image of your set S under F. So here S is some subset of your domain A. F of S, then the image of that set. This is notational because you just need to say something about what, we need some notation for the image of the set, and here it is. It's a set of points you can get to using the function f from points of that subset S. You can either write it as f of S where S is in your subset capital S, or you could write it as those points of B that you can get to using f, using some point S in capital S, and of course you end up with a subset of your codomain. If you just say the image of f, that means you look at the image of the whole of your domain. So that's just the whole of f of A. So that's equal to, so the image of S, the image of f is equal to f of A. It's equal to a set of all points you can get to where A is in A, and you could write out the other one. You could, there's a second version of that you can write out for yourself. So in analytical and computational foundations, G11 ACF, you mostly dealt with functions of one variable, whereas in calculus, you often dealt with functions of several variables. So what sort of functions would you have dealt with in ACF? F you could have from R to R, f of x equals e to the x, or you could have f from R plus goes to R, where f of x equals non-negative square root of x, or f from, could be from, say, 0, 1 to R defined by f of x equals 1 over x. These would all be perfectly good functions. Why I call them all f, I don't know, because you can use any name for your function at all, so you can put a few g's in if you want. Do that in a minute. Calculus, you had functions of several variables. Let's have g from r squared to r squared defined by g of rt is equal to r cos t, r sin t. this is actually a perfectly nice function, but actually it's the polar coordinates expression in disguise. You wouldn't normally use it for negative r, though, but there's nothing to stop you. And so on. You can write down all sorts of expressions for your functions, any function of several variables. We know quite a lot about them from calculus. You've been told that certain kinds of functions are continuous, and we're going to be allowing the standard functions and saying the standard functions you met in calculus are continuous where they told you they were. They are differentiable where they told you they were. I'll tell you a little bit about the background theory, but what we don't have time to do is go through and prove that all the standard mentioned continuous functions are continuous. I'm sorry about that, but I'll have to refer you to the books because it just takes too long to do them all properly. So if you want to know really why things like sin x and cos x are continuous, you're going to have to go to the books and find a real formal, rigorous definition of those functions and a proof that those functions are continuous and differentiable and so on and do what they're supposed to. Now we're going to generalize a bit. We're going to allow functions from r to the d to r to the l. And so from now on, d and l will be fixed positive integers, which we may occasionally specialize on for examples. And you'll just be assuming that your domain is r to the d and your codomain is r to the l, or you may work with some subset of r to the d. And so you could, for example, let's define f from r to the fourth to r cubed by f of x, y, z, t is equal to tx 1 minus t times y and let's just swap t and z over. That's a pretty boring function. Oh, I've done it wrong, so I'm going to r cubed. Let's have something more sensible then. And r cubed, let's have tz then. You can do much more interesting things than that. That's a perfectly good function from r to the fourth to r cubed. You can throw in much more interesting things like cos and sine and exp and log or whatever you want to throw in, as long as it's defined at all the points required. But in general, your first point will be in r to the d. It'll have d coordinates, and the place you're going to will have l coordinates. And you can pick out those coordinates, and that allows you to say that if you've got a function that takes values in r to the l, then it's actually made up of l different functions. And that's what we'll talk about next time, how to simplify the situation so that you're looking at functions which are taking values in r rather than taking values in r to the l. So we'll pause the recording there.